Hey everyone, welcome back. We're to section 2.7 in our business calculus class, and we are touching on the idea of what's called optimization. Now, this is sort of a big word, and what we're trying to do is we're trying to come up with the largest and the smallest. So you can imagine in the business world, we want to maximize profit and we want to minimize cost. And so when we're talking about a function, what we can often be referring to when we're dealing with just a regular old graph is something like this, where we have our f of x, and we have our peaks and valleys, they're often called. And this right here is what we're going to call a local maximum. And you can see the definition on the side there. Local is sometimes called the relative. And then here we have the local minimum. And I'm abbreviating it using max and min, which is also mentioned in the yellow narrative there that you see. And what we want to do is figure out what are those local minimums and local maximums as we're going through this. And this is called optimization. If we want to get fancy with the Latin, we say that they're maxima and minima. But all that means is that's the plural version of maximum and minimum, in case there's more than one. So let's get to some definitions. I don't want to spend a lot of time with it. But a local maximum means that all the y values at that specific x value are bigger than all the other ones. And the opposite is a local minimum means that all the y values are the smallest. I mean, they're the lowest on the graph. And let's move on to global maximum and minimum. So if we look at our first graph that we see that I drew here to the right, there is no global maximum. And by the way, it's often referred to as the absolute minimum and maximum. I tend to use the word absolute, but I'm seeing the word global here. There is no global maximum or minimum with the graph that you see here. That's usually going to be a finite graph where we have the graph of our function, and it starts somewhere. It ends somewhere else. So here's our function. And to be clear, this point here is the absolute max, meaning it's the largest y value of all of them, meaning it's the highest. And here we have a local max, minimum, pardon me. Here we have a local max right here. And we have another local minimum. So we actually need to check the local mins and maxes for a global or absolute maximum or minimum. We also need to check the endpoints. So not only is this last one a local minimum, but it is also the global minimum, because it is the lowest y value of all of the y values. And let's take a look at their graph here. So going from left to right, we have a local minimum. So it bottoms out there, but it's not the absolute or the global. Then we go up to, we have a local maximum, but it is also the global. We can see it's the highest y value of all the y values there. Then we drop down to another local minimum and a local maximum. Neither are global. There are some values that are smaller and larger than both of those. Then the very last one we see is both a global and a local minimum, meaning it is the lowest y value of all of them. All right. A lot of definitions at the beginning of this one. A critical number for a function f is when we take the derivative, set it equal to 0, and we want to know what values of a are going to make that happen. Also, what values of a are going to make it undefined. So we'll need to keep an eye on that. The critical point, once we get our critical value or critical number, is when we plug it back into the original function. Now, that's going to get a little confusing sometimes This needs to go back into the original function f of x, not f prime. There are going to be times when we plug it back into f prime, but this is not one of them. So to find the critical point, we're going to take the derivative, set it equal to 0, get the value a or a's, there may be more than one, and plug it in, and we will get our critical point. And for a local max or min, f can only occur at a critical point. Okay. Again, these are candidates. When we get these values for a, they are not necessarily going to be extremes. That brings us to our first derivative test for extremes. First, we need to find the critical number. So we take the derivative, set it equal to 0, and we get some value of c. That's going to make the whole thing equal 0. And for the first part, it says if f prime changes from positive to negative. Now, I want to kind of draw what that means. If it goes from a positive slope to a negative slope, meaning we have the slope of the tangent line is positive, and it changes to a negative slope like that, then we have what a local maximum. And if the opposite happens, and we have some graph like this, and the slope of the tangent line starts out negative and changes to positive slope, then we have a local minimum. And the sign doesn't change, then it is neither a local max nor a local min. That's a sort of a specialized case that doesn't happen very often. But we're going to want to be testing this, and we're going to do this with example 1. So the function f of x equals 2x cubed minus 30x squared plus 126x minus 8 has two critical numbers, and we're going to find the critical numbers. So I'm going to take f prime, the derivative. That's going to give me 6x squared minus 60x plus 126. And I'm going to note that I think that all of those are divisible by 6. 6 and 60 certainly are, 126. Sorry about that. And I'm going to divide that by 6. So I'm going to divide a 6 out, just to keep it simple. 6, 6, 6, and 6. And that is going to give us x squared minus 10x plus, what was it, 21? 21. That's going to factor into x minus 3, x minus 7. Which means our critical values are at 3 and at 7. There are our critical values. Now, if we wanted to find our critical points, we would take x equals 3 and plug it into f of x. We would get the y coordinate. It doesn't ask us to do this in this case, but that's okay. Let's move on to example 2. The function f of x equals negative 2x cubed plus 42x squared minus 270x plus 11. And they want us to figure out not only our critical values, but our critical points, meaning we need the y values as well. And we're going to figure out if they're minimums or maximums. This is going to get a little messy. What I've done before is I hit y equals. I've already plugged in. You can see at y1 I have negative 2x cubed plus 42x squared minus 270x plus 11. So I've already plugged that in there. We're going to do something with that in a minute. And if you need to pause the video to plug that in, please do so. All right, but before I do that, I'm going to find the derivative, negative 6x squared plus 84x minus 270 equals 0. And I'm going to divide through by negative 6 again. Or not again, but negative 6. And let's see what we get. So 84 divided by -6, -14, and -270. Here. -270 divided by -6. All right, so we are getting x squared minus 14x plus 45 equals 0. All right, this is going to factor into x minus 5, x minus 9. And so it looks like we are getting a value at x equals 5 and 9. And those are x values, and we don't know if those are local minimums or maximums. But I am going to want to keep an eye on my derivative function to figure out which one's minimum and when one is a maximum. And I'm going to do that by setting up a number line. I'm going to be here at 5 and at 9, and I'm going to pick some values in between, and I'm going to plug it into here, our derivative function, to see where it's positive and where it's negative. So I'm going to start with x equals 0. Why not? It's going to make it a little bit easier. -6, 0 squared plus 84 times 0 minus 270. And the point is we have a negative slope there. And I'm going to pick a value in between. Let's pick x equals 6. So -2, 6 to the third. Oops, wrong function, sorry. -6 times 6 squared plus 84 times 6 minus 270. Let's see what we get. -6 times 6 squared plus 84 times 6 minus 270. I'm getting 18, which the point is we have positive slopes there. And for our last one, I'm going to pick x equals 10. So -6, 10 squared plus 84 times 10 minus 270. Let's see what we get. Um, 84 times 10 minus 270. We're getting -30. Now the point is we're getting negative. Now, if we look back at our theorem here, we'll notice that at x equals 5, we're going from a negative slope to a positive slope. So that means that we have a local minimum at x equals 5. And we're going from, looking at the critical value 9, we're going from a positive slope to a negative slope. That means that we have a local maximum at 9. So now what we need to do is evaluate x equals 5 to the original function. Now, the reason I typed in my original function here into y equals is the y1 is I'm going to do a trick that I did in a previous video. I'm going to hit vars. Then I'm going to go to y vars, and I'm going to hit y1. And I want to evaluate that at 5. So that gets me a value of -539. And that is going to be a local minimum value. And I'm going to redo that, vars, y vars, y1 at 9. This is going to be -475. So we have a local minimum at -539, and we have a local maximum at -475, is what all of that means. So I know it's a bit messy. And if you need to write out plugging in 5 into -2x cubed plus 42x squared minus 270x plus 11, that's fine. Or plug it into the y equals to make it a little bit faster. That's great too. All right, and we have another way to determine if something is a local minimum or maximum, and that is by taking the second derivative. The second derivative test for extremes Find all critical values of f, meaning take the derivative, set it equal to 0, and solve for x. And so in this case, they're calling it c, which is fine. If f double prime at c is negative, then it's concave down, and we have a local maximum. If f double prime of c is positive, then it's concave up, and we have a local minimum. And if it's equal to 0, then it's neither. All right, so let's consider our next example here. We have the function f of x equals 3 minus 7x squared. Now notice that our x is limited. So we are now looking for absolute minimums and maximums. And what I want to do is take a look at, and I'm going to clear the previous function, and I want to graph. And here's our parabola. And we can see at x equals 3, at x equals 0, y equals 3. So the math should hold that out, meaning we should have a critical value at x equals 0. And what I'm going to do is I'm going to find f prime of x, and that's going to be negative 21x equals 0, which implies that x equals 0 is a critical value. Now, when I plug in x equals 0 into the original function, I get 3, which means the point 0, 3 is a critical point. All right, and what I want to do is I want to take, so let's do this, absolute, this occurs at, so when x equals 0, actually we don't know if that's a minimum or maximum yet, so let's do this. We'll use the old rule, and we'll go here at 0, like I did before. I'm going to pick something before 0. I'm going to plug that into my derivative function. So f prime at negative 1 is negative 21 times negative 1 is a positive. And when x equals positive 1, we'll say f prime of 1 equals negative 21 times 1 is negative 21. We're at negative. And when we're going from a negative to a positive, well, no problem. That means from a positive slope to a negative slope, that means we have a local maximum. Now, here's the problem. We don't know what happens at the extremes. So if we do f of 0 into the original function, we get 3. So we have the point 0, 3. Now, if I plug in the endpoints at x equals negative 4, then f of negative 4 oops, that doesn't belong, and that last one doesn't belong. So this is going to give us 3 minus 7 times 16. Needless to say, that's going to be a negative value. Let's figure out what that value is. 3 minus 7 times 16, negative 109. And at x equals the other value, x equals 1, so f of 1 is 3 minus 7 times 1 squared. 3 minus 7 is negative 4. All right. So I want to take a look at everything that we have here. And what is the largest y value? So where I'm looking right now is I'm looking here, here, and here. Well, the largest y value for sure is the 3. And that occurs when x equals 0. And what is the smallest y value? That for sure is the negative 109. That occurs when x equals negative 4. So here's our absolute minimum, absolute maximum. Now, when x equals 1, y equals negative 4, that is going to be a local minimum or maximum, but it's definitely not an extreme. The extreme means the largest y value, and the smallest y value over the entire interval, and we have to check the endpoints as well, which is what we did. All right, let us move on, and we'll use our second derivative test for this next one. So we're given a function, g of x equals x to the 4x to the third, pardon me, plus 18x squared minus 120x. And we want to find the derivative of we want to find g prime. So that's going to be 12x squared plus 36x minus 120. You notice that g prime of 0 when x equals -5. Let's verify that one, do that up here. So I'm going to do 12x squared plus 36x minus 120. And I want to find the critical value. And so what I'm going to do is I'm going to go through and divide through by 12 again. Not again, but divide through by 12. We're going to use that same trick is what I meant by again. It looks like we're getting x plus 5 and x minus 2. Let's rewrite that. X plus 5, x minus 2. So x plus 5 equals 0, x minus 2 equals 0. We get that x equals -5, and they are pointing out that g prime of x equals 0 when x equals -5. That's true. That is g prime of -5 equals 0. That's true. So if I were to plug in that -5 into the derivative function, we would get 0. That's the whole point of what we just did. All right, now we want to know whether the local minimum or local minimum at -5, and they're really focusing just on that -5. So they're ignoring that +2 for this particular problem, which is fine. So let's see if this is a local minimum or local maximum. And we're going to use the second derivative test in this case. So we're going to take the second derivative, 24x plus 36. And what I'm going to do is I'm going to plug in f double prime, or g double prime, at -5. And let's see what we get. So 24 times -5 plus 36. Looks like it's going to be a big negative number to me. 24 times -5 plus 36. Yeah, so I'm getting -84. And the point is it's negative. And if we look at our second derivative test, if we take this second derivative at the critical value and it's negative, this means that it is concave down. Which means x equals -5, y equals, did we figure out y? Yes, -180. No, that's not true. So this means at x equals -5, we have a local maximum. And they ask us to evaluate, and we get the -84. Down here, -84. Which I already did off to the side there. And the point is it's negative, it's concave down, meaning if I were to graph this at -5, we are concave down, which means we have a local maximum. And to finish up this means that it's concave down. And based on the concavity, there is a local maximum. At x equals -5. Or local max, if you want to get fancy. But yeah, so that's an introduction to optimization. There will be some other ways that we will doing some optimization as well. That'll do it for section 1.7. So thank you very much.